So today we're talking about the very rulebook for reality. I'm not just talking about numbers and shapes, but the deep, unspoken laws that math itself has to follow. And right now, there's this incredible battle going on between a century-old champion and a radical new challenger for, well, the soul of what mathematics even is. I mean, just think about it for a sec. What if all the math you ever learned was just one possible operating system? What if there's a completely different way to build reality from the ground up? This is not sci-fi, folks. It is a live and pretty intense debate happening right now over what things like a proof, a number, or even what equals actually means. You know, any system needs rules, but for math, the rules have to be absolutely perfect. For the longest time, mathematicians just kind of ran on intuition. But then, about 100 years ago, they slammed into a wall. A paradox so profound it threatened to make the whole field just collapse. At first, the idea seemed so simple, so intuitive. It was called naive set theory. And the whole deal was, if you can describe a group of things, boom, that's a set. The set of all whole numbers? Check. The set of all red cars? You got it. The set of all sad thoughts? Sure, why not? If you can say it, it exists. Simple, right? Yeah, turns out it was too simple. This right here is the sentence that basically broke math. Back in 1901, a guy named Bertrand Russell came up with this little gem. Now, think about it with me. A set of teacups isn't a teacup, right? So it doesn't contain itself. But a set of all things that are not teacups, well, that set is a thing that's not a teacup, so it does contain itself. Russell's set, this R, was supposed to be a collection of only the first kind, all the sets that don't contain themselves. And here's where everything just falls apart. The big question is R in R? Well, hang on. If it is in R, then it violates its own rule, because R is only for sets that don't contain themselves. Okay, so R must not be in R. But wait, if it's not in R, then it fits the description of a set that doesn't contain itself, which means it should be in R. It's a total mind-bending contradiction. This wasn't some cute little riddle. This was a catastrophic bug in the source code of mathematics. They needed a patch, and fast. So rising from the ashes of that crisis, we got a new system, a powerful, tough-as-nails framework that has dominated mathematics for almost a century. So let's meet the reigning, undisputed heavyweight champion of mathematical foundations, Zermelo-Franz-Scale set theory, or as everyone calls it, ZFC. ZFC's fix for Russell's paradox was honestly brilliant. It just flat-out banned the kind of circular reasoning that caused the problem in the first place. It declared that the mathematical universe had to be built in layers, from the ground up. You start with absolutely nothing, the empty set. Then you can make sets that contain only that empty set, and then sets that contain those sets, and so on, building up level by level into infinity. And ZFC enforces this with a couple of non-negotiable rules. First, the axiom of separation. It says you can't just invent a set out of thin air anymore. You can only define a new set by taking a slice of a set that already exists. So no more set of all sets. Problem 1 solved. Then there's the axiom of foundation. This rule makes that whole layering thing mandatory. Every set gets a kind of birthday, and it can only contain sets that are older than it is, which means a set can never ever contain itself. Paradox gone. And look, ZFC has been a massive success. It's the foundation for pretty much all the math we do today. But here's the twist. What if the problem was never the rules, but the building blocks themselves? What if sets just aren't the right way to think about math? Well, enter the challenger, a totally new, kind of wild system called homotopy type theory, or HoTT. Now, HoTT comes from a completely different world. It's this wild mix of logic, geometry, and even computer science. And its big idea is to just forget about sets. Forget about them as these bags you put stuff in. Instead, it asks you to imagine that every mathematical object is actually a kind of shape, or a space. Okay, this is the core metaphors, so stick with me. In the world of HoTT, a type, which is kind of like a set, is a space. An item in that type is just a point in that space. But here's the mind-blowing part. Proving that 2 points, A and B, are equal isn't just saying, yep, they're the same. No, it's about constructing a path that connects point A to point B. This one idea changes everything. And the absolute crown jewel of HoTT is this wicked powerful new axiom called univalence. And what it says is profound. It says that if two different-looking things are equivalent, if they have the same structure and behave in exactly the same way,
then they are the same thing. They're identical. In ZFC, you have to do all this work to prove you can swap one for the other. Univalence just builds that idea directly into the laws of physics for its universe.
All right, so we've got two totally different blueprints for the universe. One is built out of little bags of stuff, and the other is built out of shapes and paths. One is the 100-year-old veteran, the other is the new kid on the block. So let's put them head to head. The real philosophical fight comes down to this one idea. What does equals mean? In ZFC's world, it's simple. It's a fact. A equals B, or it doesn't. True or false. That's it. But in HoTT, equality isn't a simple fact. It's a rich structure. The question isn't just if A and B are equal, it's how are they equal. Finding a different proof of equality is like finding a whole new road connecting two cities. And this quote right here gets to the heart of why so many mathematicians are excited about HoTT. So much of modern math isn't about individual objects. It's about the relationships and structures between them. ZFC can handle that, sure, but it's kind of clunky. HoTT speaks that language natively. The relationship, that path, is a mathematical object you can study. So let's do the tail of the tape. In one corner, ZFC. Everything's a set, equality is a simple fact. Its greatest strength? It's the rock-solid, proven champion. In the other corner, HoTT. Types are shapes, equality is a rich path. Its main advantage? It just feels more like how modern mathematicians actually think. But they both have weaknesses. ZFC can feel clunky and restrictive. And HoTT, well, actually using it can be ridiculously punishingly hard. And I'm not kidding about that difficulty. For example, there's a known property of spheres. You don't need to understand the symbols, just the story. A classical proof of this fact takes, like, a few lines. The first proof of it in HoTT, it was a 200-page PhD thesis. But on the flip side, people who get fluent in HoTT say going back to ZFC feels like trying to describe a beautiful painting while you're only allowed to use the words red, green, and blue. It feels like you're working with your hands tied behind your back. So what's the end game here? Is ZFC on its way out? Is HoTT the future? Or is something else entirely going to come along? Okay, let's be clear. ZFC is not going anywhere anytime soon. It's the language that almost all of modern mathematics is written in. But HoTT is making huge waves, especially because it's deeply connected to computers and programs that can help verify proofs. And that's a field that is exploding right now. And really, this is the most important takeaway of all. The goal here isn't necessarily to pick a winner. It's about what we learn from the fight. Is the way ZFC builds the universe an essential truth about math? Or is it just an accidental feature, a quirk of the system we happened to invent 100 years ago? Having a real alternative like HoTT forces us to ask those incredibly deep questions. Which leaves us with one last massive question to chew on. Does a debate like this mean that math isn't some perfect, eternal truth we just discover? Is it possible that it's something we invent? Are we explorers mapping a hidden reality, or are we architects designing it from scratch? The clash between sets and shapes, between ZFC and HoTT, suggests the real answer is probably and beautifully a little bit of both.